Today I'm going to talk a little misleadingly, I guess, mainly about hierarchical reinforcement learning, and then a few other related ideas that are related to scaling some of these methods in slightly different dimensions. Okay, so this has come up in various discussions over the last couple of days, but RL itself is a really difficult problem. Now, if you think about some of these navigation problems that I've been pointing out, where your agent's trying to move around some room, effectively what you have is you've got this setting of a mouse moving through a maze, right? So we're trying to learn how to get from possibly some start location to a goal location, or maybe from any place in this maze to the goal location. And effectively, this little guy runs around and has to learn what to do in each situation. And you can think of this as a proxy for almost any problem you might want to care about. If you're moving a robot arm, effectively there you're just navigating in a high-dimensional space where each dimension corresponds to a joint of your arm. And similarly, you could take most problems and abstract them down to a navigation problem. But effectively, why this is complicated is typically we're asking this mouse here to remember value in each location, right? How good is each location? But effectively, the way we set it up is we typically have this mouse being blindfolded, right? So if you think about this problem and the way you would solve this problem, right, you'd have a look around, say, okay, I need to go to the door, and then walk for a number of steps, and you get to the door, and then you make the next decision, right? But typically here, or at least in the simple setups that I showed you, you've got this mouse and it knows what state it's currently in. And if it takes a step to the left and bumps into a wall, it goes, oh wow, that was surprising, I didn't see that coming, right? So it's got no look ahead, it's blindfolded. And instead it's just got to remember what's happening in each location. So eventually I've got to learn that, oh, being in this place and taking a step in that direction, I bump into a wall. And that's not a great thing. Right, so a lot of the problems here can also be described in terms of the way the reward structure generally works, right? So we've got this agent moving through its environment, and we're giving it some reward signal. Because the reward signals could be arbitrary. So I could define any of an infinite number of tasks in the same space, right? So in this case, it's kind of obvious. I want to move it to that cheese, so I might give a positive reward when it leaves the maze, and maybe negatives if it bumps into obstacles, or maybe just the leaving the maze thing. But you could define other tasks, right? I could put that cheese anywhere else. I could define another reward function that says collide with the maximal number of walls. I could define another one that says go around the outside of the maze, right? So I could define any arbitrary reward function on this space, or I could just give random rewards at different places. But typically for the kinds of tasks we think about, your rewards are firstly sparse. So most of your actions are going to give you no reward, right? So you're walking around without feedback for the bulk of your interactions. If you remember that double inverted pendulum, right? So that was swinging for thousands of time steps before it got any feedback. So it basically doesn't know what to do. It's just doing things randomly at first. And yeah, then the second problem is this is delayed. So again, there's this huge number of actions in many cases. And what happens is suddenly something good happens or something bad happens. And you've got to think, okay, what's going on here? How did this happen? So as I mentioned before, this might be in the chess case. You play for some large number of moves, 40 moves or 50 moves or something, and then you're told you lost. Now, if you don't know anything about the game, did that happen because I was playing perfectly and then just screwed up at some last critical moment, or did I just play in a mediocre kind of way from the beginning? So a big issue here is that you've typically got these long action sequences. You've got to figure out what was responsible for what happened. And often in these kinds of problems, you've got quite a large breadth and depth of your problem, right? So depending on what you're doing, you might have quite a few options available to you at any point in time. And you're looking over multiple time steps. Effectively, we want to take some optimal behavior in this setting. So if you think about navigating around, say, some town or something, you could think that at every intersection you come to, you've got to decide, do I go left, right, or carry on forward? And you can think about the number of blocks you want to navigate as being the number of decision points you're going to encounter along the way. Now, that really, in some sense, describes the complexity of the problem. In general, there aren't really good metrics for measuring these complexities, but I think this just gives a reasonable handle on this problem. But now imagine if we weren't thinking at the level of turning at intersections, and we were instead thinking about muscle activations. Right? So now you're sitting in your car or walking, and you've got to twitch a whole lot of muscle fibers to move your arms, to turn the wheel, or change gears, or press on the accelerator or the brake. Now, the time scale here is very different. Right? Instead of maybe every few seconds you've got to decide between one of, say, 3 options at an intersection, now there's thousands of muscle fibers you could trigger. You probably want to trigger collections of them so that you can control the strength of the activation. And this is happening at like the millisecond time scale. All right, so if you think about the exact same problem in that context, that's considerably more difficult. Right? And yeah, if you're thinking about the fact that you might be able to activate these things concurrently, you've now got a combinatorial number of actions. Right? So this makes this problem very difficult. So typically, if you can abstract to some higher level of reasoning, you're going to simplify this reasoning problem. Right? In fact, if I abstracted even further and just thought about go to work or go home, right? Now I'm choosing between one of, say, 2 options, and I'm going to make one decision. Right? That's a lot easier to learn with than going all the way down to the muscle activations. So there's a whole lot of different ideas you can use to accelerate this, and just for this talk, I've picked out a couple that I think are particularly interesting. But we can talk about all sorts of other ones. And I'm going to focus on, say, 3 different ideas here today. So the first of these would be to make predictions of what could happen. All right, because as I said, typically you've got this mouse moving blindfolded in the maze, and it's not really making any predictions. Right? It's just trying to learn something for each location in the maze. Any questions at this point? All right. So if we look back at the kinds of methods that I've spoken about over the last 2 days, first you've got these policy-based methods where you're trying to learn your policy directly. So that's what I spoke about, using things like policy search and deep policy search, like the reinforce method. And that gets you your policy directly. Then what we spent most of the day before talking about were value-based methods. So there you're learning these value functions, either V or Q, and from that you can derive your policy, your optimal policy, if you've got the optimal value function. So that's kind of rolling these reward function and transition model into one, and if you try and learn that, you learn the goodness of each state, you can derive the policy from this. So there's a third class of methods, which is model-based methods. Right? And in this case, what you want to do is from your interaction with the environment, you want to learn your models, which is your transition model and reward model, because from that you can compute your value function, and from that you can derive your policy. Right? So this is really trying to get to the heart of what the MDP itself is all about, and learning about this, and once I've learned about that, I can do optimal control on top of that. That's just an optimization problem. Okay, is the distinction between the 3 clear? I'll assume that's a yes. Okay, so if you want to start learning these environment models, I did mention a little bit about this yesterday, but you're kind of trying to get at the physics of your domain. So in model-based reinforcement learning, I think I said all of this, right? You want to learn these models, and you want to do so from experience, because if you can do that, you've effectively got a simulator. So if I'm a drone flying around or driving an autonomous car or something like that, and I've got a good model, then I can ask questions like, what happens if I fly directly at a tree? Right? So I can do that much quicker than actually trying this out several times and learning the value of that situation. So you can think of these models in that case as a simulator. You're trying to build a proxy of the MDP, which is the real world you're acting in, so that you can ask these questions about it. So you can probe things and say, should I do this or do that? Right? So in some sense, that becomes a supervised learning problem. Right? You're trying to learn these models, because these models themselves are just functions. Right? They're functions that might spit out either a state or a reward as a function of an input state and an action. So if you look at like the cycle of how these algorithms have worked so far, particularly the value function based method. So you're going to learn this value function or policy You're going to act according to that. That gives you more experience, and then you learn based on that. So you've got the cycle where you're improving what you're doing based on the experience. And again, through something like epsilon greedy learning or acting, you're going to gain more experience. All right, so if you can then incorporate a model into this, which says as you're gaining experience, you can learn a model from that experience and use this itself to update the policy. And in many cases, you do these two things concurrently, which we'll talk about. Right, so once you've got a model, you can plan with that model rather than trying to optimize something directly. So I've made the case for why you might want this. So in general, you want to be able to predict these things, but also it lets you reason about uncertainty, which is another recurring theme of this workshop. And so basically, if you can make these predictions, and in some cases make them probabilistically, you can keep some sort of estimate over what's going to happen. You can try and bound worst case performance and best case performance, and think about the probabilities of different outcomes. So learning your models, and depending on how you learn the models, it's going to give you all these kinds of capabilities. But in general, the basic idea is going to look something like this, right? So when we receive experience, again, this is as we're interacting with the environment, our agent takes some action and bumps into something or changes its state. We're going to do a few things. So first, we're going to update our reward estimates. So if we have a current estimate of reward, and we get some new reward signal, we can just shift the process towards there by some learning rate. All right, so this is just, at its core, a very simple idea. You're just learning some estimator of what that reward in that state and action are. And you can do the same thing with the transitions. Now, this is a little bit more subtle, but effectively what you want to do is, for the state you ended up in, you want to shift more towards 1. If you remember, this is a probability distribution that tells you what's the probability starting in ST, taking action AT, of moving to ST plus 1. Right, so it's going to be a distribution over all possible outcome states. So we're going to move that towards the one that actually did happen, where that's moving towards a 1. And for every other state that you could have moved to, you're going to shift it towards 0. Right? You can also achieve this by normalizing, but effectively this is what you want to do. You want to say, the outcome that I saw is more likely, all other outcomes are less likely. And then often what you'll do is, once you've got some estimates of these models, you're going to use these to help update your value function. Right? And you can still act according to the value function the way we've been doing before. So this is just at a very high level, heuristically, what you're going to be doing when you gather these samples from your environment. Okay, now there's a whole lot of ways of doing this, obviously. And I mean, just looking at this, all the obvious things should pop into your head. You could do like approximations to these things. If you've got like more than just a small discrete set of states and actions, you obviously can't have an estimate for every state and action that you might encounter. So you might want to approximate these with something like a neural network. You can do all the standard tricks. But the most simple way of actually using these ideas is in what's called the Dyna-Q algorithm. So this is one of the oldest model-based methods, but still reasonably widely used in all sorts of different varieties. And basically what this algorithm looks like is following a very simple kind of structure to all the other algorithms we've seen so far. For each step in each episode, you're going to do this you're going to go through this exercise of taking your Q function. From that, you're going to choose an action. You're going to take that action and see the outcome, and then update your Q function from that. Right? So that's just what Q learning looked like before, from a couple of days ago. All right, that update equation should be familiar. Now, having done that, you're going to take the sample as well and update your model, your transition and reward function. So that's your model update. And you're going to do that in the way that I described on the previous slide. So we're going to shift the estimate of reward for that state and action to what we've just received, and do the same for the S prime, the successor state. And then what you're going to do is, for some number of iterations, you're going to sample a state from this, take an action, or choose an action, and then from your model get a prediction of the next state and reward, and use that to update your Q function. So here we're sampling our model and we're updating the Q from that. Now it turns out, if you have a look at this, this is kind of doing what we were doing yesterday where we were keeping some replay buffer in the deep queue networks to sample extra transitions and use that to update your value function. Right? So as I showed in that little diagram earlier, you're using a combination of the model and the value function, using your models to update your value functions and acting according to those. This is just a very simple idea, but this works pretty well. And yeah, and you can build all sorts of other things on top of this. So as I alluded to or mentioned yesterday, you could also try and use something like a neural net to approximate these. But there was a question on other things you could do with this. So you can also learn with Gaussian processes, just because that seemed topical here. And I just wanted to throw in a couple results to show that this can be done. So in a problem that looks very much like the double inverted pendulum, it's slightly different. It's a cart pole problem. You can show that with, like, if you use Gaussian processes to learn the models, it can take you about 3 episodes to gather enough information. Because the dynamics are pretty consistent across the environment, you can use that, and after about 3 iterations with several different models, that gives you enough information to be able to plan perfectly in each case. Right? So the nice thing then is I don't need to explore all these things, because you can, as would make sense, like whatever your state and action are, you've got things like gravity, you've got the rotation of this pendulum, right? If you can learn the model of that, that applies to everywhere in the space, right? So you can just predict what's going to happen from that point. And we managed to use the same thing with very little data, like doing 1 lap of a circular track. You get enough data to be able to drive optimally on any other track you give it when you combine this with different kinds of mechanisms, and also avoid other vehicles and so on. So it actually, in many cases, if the dynamics of the problem are simple enough, it doesn't take much to gather enough data to be able to actually learn these models. Now you contrast this to what something like the deep learning models tend to do, and they tend to take much longer to do this, particularly when you're doing something that's value function based or policy based. Right? So if you try and learn these dynamics directly, in many problems that's a lot quicker. Obviously, this isn't always the case. So in some of those robotics problems, it's a lot easier to try and learn the policy, because there, in certain problems, like trying to reach for something, it's a lot easier to describe what you want to do in terms of the policy space directly. Now, one of my big personal motivations in all this work is that I find it's cool to be able to solve an interesting problem. And I mean, I keep going back to the robots because they're easy to talk about, and getting a robot to do some particular task. But that doesn't really generalize well, right? So if I've learned a value function for a problem that might describe how good each point in this maze is, right? So I spend some time moving around this environment, collecting this information, get a really good estimate of how good each point in the space is, and now some adversarial scientist comes and changes my domain. Right? So it changes what the maze looks like. I can't use any of that information to solve that new problem. Right? Effectively, you can throw all that away. In fact, you can think of it more simply. If I just move the location of the goal, right, that's changed the reward function. Right? So that said, maybe instead of giving me 0 everywhere and like 100 at the goal location, I'm now moving the goal location somewhere else. So if you think about the value function, it's a nice gradient of the value of states towards that point. If I've now moved my goal location, like that whole gradient's useless. It might be the exact opposite direction to where I want to go. Right? So taking this information from these value-based methods is not hugely useful for transferring to other problems. So one thing you could do is try and find ways of factorizing these models. Now this works really nicely in a model-based setting, because in some cases your transition dynamics might be consistent across every instance of the world, right? So I could change, for example, some parameters of my problem, and maybe the physics of the problem wouldn't change. In other cases, I might say have this pendulum and change the length of the pendulum, and that's one simple parameter change that I'd need to learn about, but I still know everything about how this problem works. So you can find ways to do that, and you can find ways to factorize this into different things. So just as an example, right, you might have some domain where you've got an agent that can run around in this video game environment and pull levers to open doors and collect keys to unlock doors and so on. But you can imagine you could have infinitely many versions of this game, right? And if I've learned something about how to solve this one as a value function or a direct policy, that's not going to tell me anything in general about how to solve other problems. So what you might try and do is do something like learn a local model. So if I can learn that if I execute a certain behavior, which might be going down a ladder, and I'm in a state that looks like this, then I end up in a state that looks like that. Right? So I might learn something about a physics of some part of my environment, and whenever I see something that looks like that, I don't have to figure out again what to do in this setting. And in particular, if you can then identify these things, you can plan with this knowledge in a portable way. Right? So you can do these as a kind of density estimation problem and learn these symbols, and then start planning in terms of symbols at a more abstract level than at each particular pixel location of your agent. Does that make sense? Cool. Then there's other ways you could try and factorize this information. So take another domain, for example. So this is called Sokoban. You've got this little agent that can run around this environment. And what he's got to do is push these boxes onto those little green points. All right, so you've got, in this case, 2 boxes over here and 2 green points over there. So this is another one of these old school computer games. And obviously, if there's something on the other side of a box, then you can't push it, right? So the challenge of the game is to figure out how this guy moves around to push these boxes onto these goal locations. And obviously, like, you could fail at this game, right? If you push a box into a corner, you can't get it out from there because you can only push and not pull, right? So now it turns out, if you look at this this game and think about all the dynamics that might go on here. All right, so what you would think about while playing this game is, obviously, if there's free space around me, I could move my character into that free space, right? So in this case, he could move up, down, or to the left, right? If there's something in my way and something on the other side of that, then I can't move in that direction. Well, to be simpler, if there's a wall next to me, I can't move in that direction. That seems kind of obvious. And then if I'm pushing a box, if there's something on the other side of the box, I can't push it. And if there's empty space on the other side of the box, I can push it. Right? And that pretty much describes the rules of this game. In fact, not just the rules, but that starts telling you how you might go about trying to solve this problem. So it turns out, if in a simple domain like this, you can learn some rules. So in the previous case I showed with Gaussian processes, here you can learn these things as decision trees that tells you what happens if you take certain actions in certain locations, what changes. You don't need to worry about the syntax here. But the neat thing is, if you learn in this simple case, so this instance of the problem has about 8,000 states. So there's about 8,000 configurations of this domain. If you think about that, you can move the agent in the 2 boxes. Those are all the configurations. It turns out if you look at this version, which is considerably more complicated, it actually doesn't look it, but there's about 1 million states for this, and the optimal trajectory for this is about 200 moves to move those 4 boxes. Now, that's a really simple level and a really difficult level. If you don't trust me, you can take a picture and try solve it later. But turns out you can learn all the dynamics you need in this thing, right? And if you've learned all of these as small portable rules of the kind that I just described to you, you can instantaneously solve that. You need 1 iteration, value iteration, and that will compute the solution for you. Right, so that's really cool. So that says that there's certain structure in problems that you can leverage if you learn the rules in the right way that let you solve far more complicated problems. Now this ties into all sorts of other ways of thinking about problems in reinforcement learning. In particular, one that I really like is called curriculum learning. Can I design a curriculum of different tasks that get progressively more difficult that help me solve the more difficult problems that might not have been tractable if I just started off with those problems? So most of the kinds of methods that we look at in this space are really to get around this problem of transfer. But of course, there's the questions of how do you represent this information in a way that lets you take it into these other instances of the problem. Okay, so that was just a bit of an introduction to some of the ideas in model-based reinforcement learning. But now I want to talk about something else. So I've started speaking a little bit about exploiting the structure, right? And so really what we were doing there is relying on the fact that certain sub-pieces of your problems keep recurring in different places. Right? But similar things can happen structurally in your action space. So what I mentioned earlier is you've got this challenge where if you're thinking about a problem at the level of muscle fibers and activations, your problem's way more difficult than the problem we usually deal with. Right? That's not how humans tend to think about things. And the way we deal with this problem is by having different levels of abstraction. Okay, so if I task you with going to that downstairs area to get some food, you're going to think in terms of, possibly if you know the place well enough, of just going there directly, and you might be able to do that blindfolded. But otherwise, you're probably just thinking in terms of taking a couple turns. You're not going to think about this at the level of muscle activations. But if then suddenly some sneaky person had constructed some weird obstacle in the way, you'd have to drop to like a lower level of control to climb over the thing. Right? So you're generally operating at the highest level of abstraction that you can, and dropping down to lower levels when you need to like patch something or deal with a problem you didn't anticipate. So what this kind of tells us is that we should think about the way we're acting in the environment at different levels of hierarchies. And we typically talk about this as skills. So if you're acting in the lowest level, those are your actions, but you can structure your actions in different ways to get skills. All right, so these basically then become components of behavior that you can synthesize in different ways and treat as discrete actions. So this gives us a way to think about behavior in like a modular way, right? So if I have like a control program that lets me go up and down a staircase or lets me walk to the end of a corridor, I can think about these as compositional units that I can piece together to reason about my behavior at a higher level. Right? And so this comes back again to this idea where instead of solving a single problem monolithically, we want some sort of transferable piece of information that we can reuse. And in this case, I'm going to talk about one particular flavor of doing this, which is hierarchical reinforcement learning. And under hierarchical reinforcement learning, there's a few different frameworks, but one of the most popular is to use what's called macro actions. So this is this idea that I want to be able to take my lower level action primitives, structure them in some way, and then reuse these. And it will turn out that then what we've effectively done is factorize the problem, not in terms of these visual components, but in terms of behaviors. And each one of these is in turn itself a reinforcement learning problem. So as I say, there's this one particular framework I'm going to talk about, the options framework, which has a lot of nice theoretical grounding, and actually isn't that different from the standard way of thinking about reinforcement learning. Okay. So what we're going to do here is define what's called an option, and this is what you can think about it as like a macro, the way you might use in Excel or if you're programming or something like that. And this is going to be a temporally extended action that acts as a little mini policy, right? A little mini behavior. And formally, the way we can define these options is with a tuple of 3 elements. So the first is going to be an initiation set. So that tells you a set of states in your state space where you could run this, right? So it's just like an indicator function that says I can run the option from the state. You can think of this intuitively as like if I've got an option to go down some stairs, I can maybe only run that from the top of a staircase. Right, then you've got a termination probability. So you've got a probability defined over each state that tells you where might this option end. Right, so if I start going down the staircase, it might end with like 100% probability right at the bottom, or it might end with some distribution down the stairs. And then finally, you've got some policy, which as normal is just going to be a mapping from states to actions, or a distribution over your state action space. So these are the 3 basic components that go into a standard option. So now you can think of these 3 things together, this option, as this little policy unit. So what does this mean? If we go back to this domain we've been talking about, we've got this little agent moving around some environment. Now you might decide somehow that it's useful to be able to reach that door in the middle of the domain. Right? So maybe being able to get to that door from anywhere in that first room is going to help me solve the problem. And that seems plausible, right? Because instead of having to make a few decisions beforehand, and I can do one thing that'll solve half the problem for me. So what I would do then is I would learn this option that basically says, for wherever I am in this first room, this will take me to that doorway. And in the way that we had a goal in the previous one, we can think of this as a goal in this doorway sense that is kind of chaining these two problems together. So the three components that I mentioned, you've got this initiation set. So in this case, anywhere in this first room, I could run this option. Right? It doesn't make sense to do it from somewhere else. Then I could have a termination condition which terminates with probability 1 in that doorway and 0 anywhere else. And then I've got a policy which just tells me how to move around under this option. Right? So it's a tiny little program that's solving a small version of a reinforcement learning problem. Everyone following? Cool. Okay, so I did briefly mention that was a Markov option. It doesn't have to be. And this won't really go into. People don't use it a huge amount. But you can basically have different versions of these options that do other things. So you might have options that instead of being a policy over your state action space, do other things. You could say run for at most n steps, or do something n times, or have any other internal indicators of something, right? So it doesn't have to be defined in the way I've defined it there. You could just think of this as a program with some arbitrarily complex logic. So you can do things by defining state machines and all sorts of things, and it gets quite exciting. But people tend to not actually do that because most of what we need is encapsulated by the standard Markov options. Okay, so the next important thing to think about is your standard actions. So your primitive actions, which would be in that case your move up, down, left, right, are actually each options in themselves, which is pretty handy. So all of these typically have that they can be initiated from any state in the state space. They'll all terminate with probability 1 at every state, because they're only going to run for a single action. So any state they end up in, they're going to terminate there. And then the policy is very straightforward. It's just doing that action. Right, so any primitive action is just a one-step option. So it means that it can be executed anywhere, lasts exactly one time step, and always chooses action A. Right, so the nice thing now is if we look back at this problem, effectively what we've just done is augmented the action space to say that instead of having these 4 primitive actions, we've now got 5 options. 4 of them will move the agent in one of the cardinal directions, and the 5th one will take him to that doorway. Right, so we've just augmented extra actions onto the action space of this agent, but some of them run for longer periods of time. So now, if you're given an MDP, you can just effectively swap out your action set for your option set, where your option set is strictly larger than your action set. And then you get to reason about this in a whole different way. So you can ask all these sorts of questions about this. So there's ways we can characterize the problem, which I'll talk about next. And then you can do all the standard stuff. You can plan with this, you can learn with this. And actually what's still very much an open question is, how do you learn these options? So I just mentioned that going to that doorway might be a useful thing to do, and there's good reasons to think that that's a good thing to do. Particularly, you could look at something like the connectivity of the state space, and that doorway is a bottleneck state, and you can learn options that take you to any interesting bottleneck states in your space. But that's just one principle you can use for learning options, right? There's a whole lot of things people have tried, and it's still not clear that there's an optimal thing to do. Okay, but if we've now started thinking about options instead of actions, that gives us a slightly different framework. So instead of using an MDP, we now talk about an SMDP, or a semi-Markov decision process. So this is very similar to an MDP, right? It's got all the same things. It's got your set of states, it's got your set of actions, which in this case are options. It's got a transition model, it's got a reward function, and it's got a discount factor. So the only difference is we can now think of these things as having time durations. Right? Because I might have an option to leave the room, and that's going to take a different amount of time depending on where I start executing it. Right? It could be one action if I'm in the doorway, it could be quite a lot if I'm up here on the stage. But typically we keep this thing fairly simple. We think about these times as integers, and that particularly makes sense in the discrete case. There's all sorts of other things that happen in the continuous case, but there's many open questions there too. And yeah, the semi-Markov means that it is Markov if you take into account that your transitions can last for some longer number of time steps. And then turns out you can just use the same kind of reasoning about this. We can go back to the Bellman equation that we had before, which gives us this nice recursion between the value of an option in a state and the value of the option in the next state, of all your actions in the next state. You again have these components of looking at your immediate reward and looking at the expected future reward. And here you're doing the same thing we were before. We're saying that the value of an action or an option in a particular state is the sum of my expected immediate reward, so the reward I get now, plus the value of the state that I end up in, and we look at the whole distribution over those states. Right, so the nice thing is you can reason about these things using the same kinds of mechanisms we were using before. And what's handy about that is we can then use the same kind of algorithms. Right, so when you're learning, you can again learn from taking stochastic samples. You can use this Bellman equation for simple iterative methods. You can do a similar kind of value iteration. You can do all these things in the way that you'd expect to be able to be done. So there's a lot of nice theory that just ports across to the options case. All right. So if we have a look at an example, right, so you might have something that's a little bit more complicated than the one I've been showing you, where you've got your 4 primitive actions, as you often do in these situations, but you might also have 8 multi-step options. So let's say from any room, we've got an option to go to the one doorway and an option to go to the other doorway. Right, so that seems a useful thing to have if this is the environment we're going to be spending some time in. And then obviously your options then would look something like this, right? So the option for this top left room to get to the door in the middle is going to be this vector field. So if we follow those arrows, that's going to be executing this option. So we can run it from anywhere in this room, and it'll be this policy that takes us to that target hallway. Now you can see some of the benefits of doing this in a couple little illustrations here, right? So if we were just looking at the primitive actions and looking at the way the value propagates. Now remember, in the standard setting, we discussed that there's more intelligent things you can do. Each time you encounter a state that tells you something about the value of the previous state, right? You're doing this backup of one state. So if you look at the propagation of this value back from there, right, you're looking one step away on the first iteration, and then 2 steps away on the second iteration, and so on. Right, so you'd have to run a number of iterations to get this value propagating around the whole space. But if you only look at these hallway options that I've just mentioned, right, if we were looking at, say, the goal being to reach this hallway, now with one iteration backwards, we fill out those 2 rooms, and one other iteration we filled out the whole space. Right, so because we've got this modular information, we get to reuse it, and much quicker get an idea of the coverage of the value of the space under those options. But obviously just using the options themselves wouldn't be completely useful if we were ignoring the primitive actions, because now if my goal was somewhere in the middle of one of the rooms, I wouldn't be able to reach there. Right? I might stochastically reach there if I run options to move around that room enough and I'm lucky, but in general it's not going to work. Right? So if you use both, then you just get the same kind of effect happening anyway. Right? So it gives you a way, effectively you can think of this as reducing the diameter of the problem. Right? So you could almost collapse all of these states in one room into a single point. Right? As long as you were just transitioning through that space. So there's just a couple of things to note about these. So what should be obvious, if you've got a policy in an MDP, so standard MDP just with primitive actions, that's going to be a Markov policy, right? Now if you've got a policy over an MDP with options, that could also be Markov, but not necessarily, right? So you might not be able to to be able to predict things in a Markov way if you're running options. And I'll show you what this means here. So you could have one option in this environment that takes you to the top hallway, and another one that takes you to the other hallway. But if you look at this place where they overlap, you don't necessarily know what's what's happening there, right? The value will depend on what option you're executing. So when you're thinking about policies in the space, it's usually useful to think about what option you're currently executing. Blah, blah, blah. Okay, yeah. So in many cases, when we talk about this being semi-Markov, we're referring to the fact that if you're just taking a primitive action in a non-option land, then what you're doing depends on just that state under your policy, but now it depends on what option you're currently executing. You can't just tell what action I should be doing at this point just based on the policy. It depends on that option. Okay, so this is basically just taking the problem from being in an MDP space to an SMDP space by adding these options. And so now this gives us a nice mechanism for reasoning at different levels of abstraction. Okay, so if you take that previous example that I gave, you might have a whole lot of options that talk about how to move my arms and legs to drive my car. And now I can think about, reasoning at the level of turn left or turn right, brake and accelerate, where each one of those higher level decisions that I take is actually executing a whole lot of lower level actions. Right, and then there's all these other things you can do, right? So you can add new options, you can update them, you can learn with them, and there's mechanisms that allow you to interrupt them as well, right? So you don't have to run them to termination necessarily. With a few small adaptations, you can interrupt your options prematurely. So this gives you a way of thinking about skills. So we're not just operating at the level of raw behaviors. We can structure on top of this. And this has all these benefits, as I mentioned, reducing the diameter and the branching factor of the problem. This really helps for exploration, right? If you think about what happens if I'm exploring randomly, I'm taking single actions and just moving around. So if we're just at the beginning of learning and we're acting completely randomly, you're going to execute like this Brownian motion moving around this domain. So if you start off in like the bottom left corner, it's going to be quite a while before you've randomly wandered your way out into other rooms to explore things. But if you've got these options that take you to these hallway points, you get a much faster coverage of the space, and you tend to learn a lot faster because of that. And then you can do other fancier things. So recently, people have started looking at ways that you can build even higher order options. So in this case, you might think about this driving example, right? So instead of thinking about moving your muscle fibers, you might think of, say, turning the wheel. Instead of thinking about turning the wheel, you might think of turning a corner. Instead of thinking about turning the corner, you might think of getting to particular locations that you know well. So you could think about your behaviors as not just these two tiers of just primitive actions and options, but a whole stack of these things. So you might learn, for example, at a lowest level, how to navigate between individual states of some environment. And then you can think in terms of rooms and houses and communities and think about this in a very structured way. And if you learn something about one environment, you can share that knowledge with all your other behaviors. All right, so that's just a bit of a whirlwind introduction to thinking about behaviors more hierarchically. But I think the core takeaway from all of this is that what's really important if you want to do this work in these different settings is to be able to reuse knowledge. All right, so using modular pieces of models, using things like options and higher order behaviors gives you a way of reusing knowledge that you can transfer between problems. So this is the whole area of transfer learning, which is I want to be able to use some experience I've gained while solving one problem to help performance with another one. Right? If I've got an agent that's learned to navigate in a set of rooms or a set of buildings, and I now wanted to do something in a different building, there should be certain amounts of knowledge that it can reuse there. Right? I don't want it to have to learn bumping into walls is bad all over again. So options gives you a nice way of thinking about this because you can do all this kind of skill transfer, but in general there's lots of different ways you can think about transfer, right? Effectively what you want to do is take some components of your knowledge and apply them to different cases to help you learn in those situations and learn faster in those situations. Right, so the general principle here that we're leveraging is that these subtasks reoccur across problems. Okay, now in general this isn't the case. So we typically make these assumptions that like a family of tasks you care about are drawn from some distribution. Right? If you've got a robot that's learning to pick something up, you're going to assume there's some distribution over the kinds of objects, which is going to affect the grasps and how transferable they are. Right? So you might pick up a bag in a very different way to a cup, and those skills might not transfer there. You might be able to use one skill for some distribution of locations for picking this thing up, but if it's in too crazy a place, you don't expect it to transfer. Right? So all the standard kind of assumptions you want about task similarities apply here. Right? So if we want to be able to solve classes of problems, we need to make these kinds of assumptions, which again isn't something that is very well characterized. This is still open questions of how do we talk about task similarity in a way that we can reuse knowledge. But generally, if you can reuse knowledge, you want to see this kind of performance. And you do see this kind of performance under the right settings. So if you just learn something from scratch, you might get a curve that looks like this black curve here. If you've learned some options, you could get a much better performance. And typically, you get this, what we call jumpstart performance. So there's a big gap in the initial performance. And this is usually useful in reinforcement learning because that big gap at the beginning is all the bits where your robot would have fallen downstairs or you would have tried to give your patient 12 kilograms of medicines or something like that. So these are the things that you don't want to do at the beginning. You want to use some prior knowledge to transfer across. And if you've got the perfect or ideal options, then your learning problem might be trivial. Right, so this is a case where transferring knowledge across between problems, possibly in the case of a curriculum or something like that, or moving from a simulator to a real environment, gives you these kinds of performance improvements. The other property you typically want to see is that the more of these situations you've encountered, the better your jumpstart performance is. Right, so if I've had 0 previous experiences that I'm transferring across, I'm acting from scratch. But the more I've seen, the more knowledge I've got to transfer. Right, so it should be pretty clear that there's a lot of different kinds of benefits you might get out of this. So I mentioned there that you could get this jumpstart performance, but you can also improve learning speed. Sample complexity is a big deal for expensive systems. And even in the right situations, you can get better asymptotic performance. Now, I've just touched on this idea of transferring knowledge, but there are quite a few different things you could do. So there's an idea of structural transfer, where you can transfer some knowledge about the structure of your problem. This might be typically in the representation of the problem. So this could be some piece of knowledge that we can take and reuse, whether it's something about the action, something about the rewards, something about the dynamics, or even something like what are appropriate basis functions to use here, or the kind of weights of a neural network that might be appropriate for a class of tasks. So something about the structure in general that we might want to know. And on the other hand, we could transfer experience. All right, so you can use pieces of value functions or policies or samples that you learned directly or you experienced directly in one setting, you could carry across to another setting and reuse there in some way, often to act as like more training data or something like that. All right, so I've spoken a fair bit about why we want to do this. One of the settings that I'm particularly interested in is this idea of multitask learning. I find it particularly uninteresting and very 60s-ish to get a robot that learns to do one problem really well, like hammer in a nail or pick something up. I think what you really want is something that, you know, the ideal fantasy sci-fi setting of you get your robot arriving at your house and then you teach it how to mop the floor. And then it does that for a while and you decide, I'll teach it how to sweep the floor. But now it should get better at sweeping it should be easier to learn to sweep the floor if I've already learned to mop the floor. And if I then also learn to sweep, I don't want it to unlearn how to mop, which tends to be the problem. You get this catastrophic forgetting effect where if you teach your system to solve a number of different problems, it forgets the earlier ones, right? So you want it to stay good at the previous ones and possibly even get better at them, right? At this point, it might have learned more about using tools and using like long cleaning implements with handles and things. So the more experience it gets, you'd expect it to get better at all these related tasks. So that's where a lot of the interesting research is, in my opinion, at the moment. And I mentioned curriculum learning before, and this is also very useful. So this is an old problem that people still use, which is the keep away problem. So you could have, this is a top-down view of some robots playing a small piece of soccer. So you might have a team of 3 on 2 that just have the goal of keep the ball away from the other team for as long as possible. And turns out you can get very nice results if you learn in that setting and then transfer to a 4 on 3 problem, for example. Right? But then there's all sorts of questions about what's the mapping between variables. You could think about the variables here might be things like the distances and angles between the agents. But now when we move to the more complex setting, like there's different ways you could think about that. So there's all sorts of representational questions that you should learn in this case. Right, so, and then the benefits, as I mentioned, are really what you'd want to see in long-term performance. If you just care about a single task, then just learn how to solve that single task. But a term that's often used quite a lot is lifelong learning. So if I've got an agent that I might give a series of tasks to over the course of its like operational lifetime, you'd expect that as it sees more tasks, its performance gets better over time, right? Because it learns more about the environment. Just as an example there, if you have only learned to solve a single task, it's very hard to say what that I'm doing is a function of the physics of the environment, and what that I'm doing is this task specific, right? So if I'm trying to get to the doorway, like the fact that I would have to walk between the desks isn't really a feature of that task, it's a feature of all navigation problems in this environment. But you can't really tease those apart if you've only solved one thing before. Okay, so just what I've tried to do here is just give a kind of brief summary of different ideas in the space that lead to these ideas of transfer and multitask learning, particularly looking at model-based reinforcement learning, as well as action abstraction with the options framework. And all of these start giving us a handle on being able to solve more interesting classes of problems rather than a single problem, which is the standard reinforcement learning situation. So with that, I'll wrap up. Thank you very much. Hope that was interesting.
Thank you, Benji. Any questions?